network and how we want to use related platforms. Which we can follow and then we can build the account models to do it. And we quite easy for you to go for any related sequence. And we just welcome Gautham. He's going to give a demonstration on the ROS robot. So we have the ROS bot. So which will have more insights on how you're going to use with your the robots using the ROS platform and how we'll be giving a demo on the custom built bot from our lab, which we have designed by us, and then we have built it completely right from scratch, and then customizations and how we can create it. So this will give a complete briefing for how you can build your platforms. An overview over ROS, the hardware we are using, the system architecture, which is designs, and then we'll also be showing you a result, which is a live demo of the ROS bot working. So, what the ROS bot is actually used for, that can be used as a surveillance bot, multi-layer surveillance bot, because it has LiDAR, and then we are incorporating cameras in the future, which will help you detect intruders and educational, as this is a multi-layer platform, so we can add platforms and then can be easily modified. ROS or robot operating system 2, even though it's called an operating system, it's more like a middleware software. So it acts between the code in your laptop and the software. It has a real-time distribution services and it is multi-platform. It works on Linux, Windows, and also the one-core computer, Raspberry Pi. When you use Linux, so it will be as we get a Linux. And then the tools we are using are others, Gazebo, Twin, as Sar also explained. Gazebo also uses digital twin as well as others. Gazebo, it's more onto like you can replicate the atmosphere, everything else. Others, it's more onto the sensory data, everything else. And this is actually a small model. So, under some flexible algorithms, you can import models which you have already built. Coming to the models we are using, import computer is a Raspberry Pi 4. We are also using a PC 2.1. So, this is also a microcontroller or basically differentiate between both of them. So, put it simply, one will be the brain of the board, and then this will be the nervous system. So, this is way quicker. This will get the info from all the sensors, LiDARs, IMU, everything, and then feed it in an easy way to the Pi, which can send it back to the core. And then LiDAR has started explaining more of very good yesterday. So we are using LiDAR that also has range. We are using a great number of local. This is the battery data. It's the 11-volt battery. And then coming to the drive, this is a custom drive which my senior who worked on this, he made it in the starting only in the Fab Lab here. He made the model in the SolidWorks. Let's product that describe the rover. So the bottom part of the yellow color you can see the drive below. This is a custom. It was you can see it was assembled. He built it and then got it fabricated from the Fab Lab and started only. So it's an in-house built project only. And then this is a flowchart explaining basically. So we have now the computer which has the board which will run. And then you can see how the rest and the easy so it easy to get all the information. This is the IMU voltage sensor and easier to also connected with motor drivers. This is the each motor. There are two motor drivers. Okay. So easy access the main nervous system. It gives all the information from all the motor sensors. And then sensible adjusted. Also, Lisboa and camera are their own connected to system because online listening is a visible account and then which is also connected to system. This is can you go to the previous slide? So, what is the configuration of that motor driver? This is just a software. Yes, sir. What is the software? So, motor driver also, uh, you can see the bottom that is also custom built by him. This one is the four-wheel drive. No, basically four-wheel drive, but then each wheels will so in the code when you're turning because it doesn't have axle, so it can't turn. So each wheel will be turning. So when it needs to turn, so you know how four-wheel drive doesn't have an axle, one wheel will turn more than the other to initiate the turn. Like if you are turning, so maybe if you're turning left, the left wheel will spin like comparatively less than the right wheel. The right wheel will spin faster so that it can initiate the turn because it doesn't have the axle so to turn around. You can see in the overall it actually has the axle, so it can easily turn around. And then this one we have the Gazebo model. This is the Gazebo model we built. It is a way. Then mostly I think we can handle the way. Before that, what is others? Other way I'm going to show my output. Others or the phone visualization tool. It is in ROS to basically use the GPU. Others will show one, two, three data and everything, and also you can basically do a robot model. So you can build a simple model like this. So this is the GPU, but then the model is a bit more defined. This is the ROS 3. You see when you simply look at the model, you can different model when you are on the next. Last two, so while others is basically very convenient in Ubuntu only because the last one can be Ubuntu 22.04 version. And then when you install last two, it will also install as a row with last. And then you are here or you can go the specific formats, which is about hardware and the it's what you want to so you can actually build the same I can actually build the same model in Gazebo. Others, if you don't want to show me a selfie of the I'm showing a live demo. You can see the LiDAR, the live demo showing up. And mapping also, it doesn't really mapping. You have only the also done the 2D mapping. The video on the other hand, if you want to simulate so I have to make a simulated thing. The camera mount. And then just deploy that robot. It will work. This is multiple cameras similar to HDR, so it doesn't need normally it's a structure. So to create this kind of model, and then ours is these are the major point agency interact with the standard focus camera measure. These are very basic tools. You can interact with the phone. The phone can have usually these things. There is a button. So the add button has most of the features. So after you use this, how to deploy the robot model to the using the camera. So every time we have to open each of these, which will show what all we are using. If you get the live demo, first thing I have to, we are using a pile, so I'll SSH into the pile, and then we have a list of commands. How to launch Rviz, and this is going to run and type Rviz too. It will launch Rviz. The robot running live. As you can see, the LiDAR is also working. So So, yes, so this is the 2D LiDAR working, and the laser scan, you can see the red lines. So everything connect to that. There is also IMU and ODO, so if you turn with it, it's also affecting the camera. So you can see the LiDAR also working. Those reflects. What is supposed to reflect? That is the laser scan. So you have that is how the laser scan gets back. Yes. So because it's a memory cell, that are obstacles for it. Yeah. So if you put it in a flat, what is the grade there? That will see the map. So if you put it in a clean background, it will somewhat look like this. So that's what actual 2D mapping of the diagram. So of course it goes for an environmental mapping. Any object outside and close proximity to that, so that gets run to the other one. So feeding with the red lights and other things. So if that what is close enough to that one. The more mapping is with your complete environmental mapping. First thing it does with the environmental mapping. You're doing that path planning that it goes on it and identifies what is very close to it. Right, deployed, keep it there. So the red lines basically these are fucking calls. So they are not moving, so they will just mark it darker, and then if it moves, it will change according to the map. The darker ones are walls because they haven't moved yet, or and then lighter ones are just there's nothing there, so the bot can move there. If there is black, that means there's suppose I keep an object and then it becomes outside, that is with that. This is any part of the space. It's great. Those darker elements are block plane surfaces. Suppose we have it there, and each and every one, if a person is sitting. So that visibility is very low. Then that creates an environment pattern there. Then again it flows further. Now this limited voltage. Yeah. So that is the close proximity. Lasers there, these lasers are so if now I'm just keeping up there, you can find that nearly let us know. So if it just move with that part, it is going to be because we need to go for some time because the demand is just getting into the rotation sequence. So it takes few seconds to be able to scan it again. The real scan will be real time. With the mapping, it will try to map the first time you turn it on, and then it will replicate that map only. Yes, nowadays one is using only with the radar. Actually, this we have made for a custom build for. So any kind of sensing that we have to do, we can add it. One is with the radar, and now we are working with integrating with vision and then with the radar. Yes, both are being not that we're using to build a map, taking both inferences. The reason is if we have this radar, it is just recognizing after this first level, not the lower surfaces. Because that we find difficulty in navigating through unknown environment. So it has a range. So only beyond some 30 centimeters it we are able to capture. So whichever it is close proximity, it is not able to capture. So they have environment. So now we are fixing up the camera or the flashlight to have a close capture. So if you have the now we are looking at the algorithm to capture the front visual part along with the LiDAR's one. And that we are going to synchronize that part. So that gives a complete solution for this kind of problems. That sensors that is more any possible one when we can add again. That for the initial models. No, actually, what we have made with the this is a stackable module. So where we can add any kind of sensors to it. Suppose I want to have with multiple measurements. Even I want to go for some sensory one. So I can add that module to this. So this will give a complete solution for any kind of purpose. So this is platform to integrate any kind of sensors as well as the. So this one we are not gone for a steering input. So when I go for a steered sequence, the cost is high, and I have to go for a lot of design and then with integrating. So we went only with the 4-wheel one. So which using with the axis movement, I can control with the turning sequence. Just with the 4-wheel one, using with the motor control. So if I hold with the wheel N and I want to move the other two wheels, I can give a rotation sequence. So that's how currently we are working on it because the axis cannot rotate. I cannot turn it. So I'm just using only with the normal drive sequence to do it. And if you want to have other control, you can replace that one. So if you see this also, we have a platform, the stackable module for integrations. So whatever you want to have it, even at the front, you can have the other sensory ones. So that we can mount here and then we can take the input. So now we are planning to mount the camera here and then record different visual inputs. Yes, yes, ma'am. Mini self-driving, and we want to explore. We are exploring more onto that. So autonomous drive, it's where people cannot get it. Suppose because we have a remote and any monitoring we have to do it. So there we can deploy this, and we have a control on our RVS platform. Because the RVS, we can give a real feed of the sensory data to the RVS. So Gazebo, we can go for a model building, and for the RVS, we are taking the real-time data of the sensors to give a feed to it. So that's what my previous student Hari Krishna and now Gautham, they are working on this. So we are building up that particular input and giving a real-time feed input. So which will give the complete parameters what we want to measure it. Suppose if any harmful gas is there, can you fix up with the gas sensors at the front and then you can deploy it. Because the safety is a priority. So we want to have the high safety system for the Kubernetes. So we'll deploy that and see how the environment does. And this one doesn't need a GPS. We can have the localized platform. So if I just have just with the connectivity and with the battery support, we can deploy it and then look for any solutions. Yes. Yeah, digital twin model. It's a digital twin model. So I'm just deploying in a remote environment. So that we are showcasing in the twin environment here at this system. Definitely. Anything we can record, but based on the requirement, application requirement, we have to fix with the sensors. And now we are integrating only with LiDAR, we are able to do with all the planning and things. We are using with the Hector SLAM. So the SLAM also we are using with a very simple model, the Hector SLAM. So that is quite easier to devise the path planning. So you have multiple SLAM algorithms, but we are not going for the complex environment. We are taking with the limited sequence because we don't want to put heavy complexity on the path planning. So we are reducing the path planning side and then deploying it. Basically, ROS used for digital skills. Yes, okay. So there we get the real sensory information, and that will show in the digital twin environment. So we can suppose if the temperature side, I can fix the temperature sensor on the panel, and if you are getting it, and if it is on the high temperature, here we can give some warning or kind of information. So how the temperature gradient is there. Actually, we are not following with the gradient-based principle. So what is that? We are identifying what are the common objects present inside. Because that is the initial scan sequence we have to follow. So once if you put the code inside the environment, it goes for the complete scanning. And identify where the objects are there. And if the object is in the mobile environment, that also gives a data. Close when I'm having some of the something here, and if it starts moving and then goes for other environment, that also can be scanned. So that scanning, I can identify some folders there. So based on that, I can change my partner. So my what is the thing is so suppose I want to go for a complete scan, how I can go for the device. Okay, complete program. Once the distance you can control where I want to move there. So I can use with your screen environment. So that I can one of the things I want to scan inside the environment. So that we can do it. And then we can go for the part. Suppose I want to go and fix at some point. So I can give the input where I want to stop. So if I give that part, so that also it will remove that part and stop there. Because few things, if I want to go for some other thing, you stop there and then you can again search it. So what kind of information I can like that. So that's very important using this part. That's why the main model is we want to have the ROS platform and connecting with the Gazebo model simulation. So that's what we are doing for the relation rendering. Then how our platform should be there. And now what we are showing is only with the other side. How the data real time it is happening. So we want to see that still larger also we can scale it. So what will be the real input from there? And then we can provide it. Because the Gazebo integrated with all this data, I can visualize what we want to have. So the visualization part and the data can be synchronization. So that we can do it. So you can connect the Gazebo output to this circuit. platform we are having, building the so that's it. And these are the models which we are going to support it because if you want to have vehicles and parameters, like if you don't get data, so we can use the to parameters and have this data I can infer to the vehicles. Programming for coding is what as you are explaining. I think basically use CD sequences or Python, everything, and then the code will be large only. With launch files, everything, it will be sent to the file. What we used to do is it will scan, make a map, then 2D purpose is what we give. So the map is currently a bit messed up because there are a lot of obstacles, moving obstacles. If there were fixed obstacles, the map would look like the other one, this map. And then 2D purpose, that is how we used to move the board. If I have an obstacle here, if I give the 2D purpose like this, the arrow pointing means it will go there and then turn its head towards facing here. It will avoid the obstacle, go around it, and then face there. That could be also used, but then for that, I'll need to add shocks and magnet flow, which, as it is a scalable platform, you can easily add more kind of wheels, which will enable it to move very freely. It can move even sideways, which is all future plans. Mechanism wheels. Something. Yes, it can have mechanism wheels, it can move sideways. It can move freely. So, it can move. It's independent of that side. This project was actually built by a senior. I joined this lab in my first year, so maybe 4 or 5 years. Initially, he built this for the education purpose. That is why the scalability and not directly the product. But then we are trying to change it, and then that's why we are adding a camera. So a 3D LiDAR also can mimic it, but then 3D LiDAR currently are way more costly. So instead of this, if we add a camera, it can mimic the programs what a 3D LiDAR does. And then also the camera outputs will be also shown in our. So you said 3D LiDAR and camera for 3D LiDAR. Somewhat maybe. 3D LiDAR can also capture what's behind it, the 3D objects. Camera, it will have to turn, but then way more cost effective. Stop. That will also stop there. And the track proportion starts here. And that's obstacle just be kept for the scanning. So it goes and both the things here are here on this platform.